Okay, so where we left off was we were looking at the errors in approximating the function sine of x using the fifth degree Taylor polynomial, also the Maclaurin polynomial. And what we saw was as long as you're close to the center, which is at x equals 0, the approximation is very good. Once you start moving away from the center, the approximation is gradually worse. And so what we did was we found those errors and again indicated how small it was when we were approximating sine of 0.1 and not so good. Oh, sorry, the error was much bigger when we were approximating sine of 2.5. And then we noted that the maximum error would clearly occur if you're given an interval around the center at those endpoints, right? And you can see that from the graph. Once you start moving towards pi and negative pi, the functions start to notably separate. All right, so we're going to take a little bit of a closer look at this idea of error, and we're going to actually look at a graphical approach to analyzing the error. All right, so this is how can we graph the errors on the interval negative pi to pi? Well, all we're going to do is we're going to notice that the error, so I wrote it in Desmos, you'll see it like a function. So I'm going to call it like e of x, and I'm going to write here e of x is equal to, so with our errors, we're just considering the absolute value. So I'm going to put sine of x minus, and I'm going to subtract the fifth degree Taylor polynomial. And again, just a reminder, all that is, right, it's x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. So this graph here is going to give us what the errors are. And so let's take a look at what that is, and then I'll replace this blank graph here. I'm going to delete it and replace it with a screenshot. So let's see. We've got, so again, what I have here is I graph f of x is sine of x. There's our fifth degree polynomial. And then I put in absolute values, f of x minus p of x. And then I even just restricted my window to be in between negative pi and pi. Okay, now that's obviously optional, but let me just snag this, and there's our picture. Okay, I'll put it right in here, make it fit. Okay, so there's our errors. So we should take a minute and reflect on why it has this shape, right? It makes sense that it would have this shape because this is the graph of the errors, right? And so the errors are 0 at the center. And then as you move away in either direction, the approximation gets worse, so the errors grow. The maximum errors occur. We already established this. This is the interval negative pi to pi. Make that really clear. We've already established that the maximum errors occur at the endpoints. At the endpoints of our interval negative pi to pi. Okay. All right, so then it says, what is the maximum error on this interval? So we know where the maximum error occurs. Let's find out what it actually is. And I'm trying to prime you a little with some notation here, right? I'm really trying to get you to see that the error can be written like this. So the maximum error, or max of this, would be less than or equal to, let's just go evaluate our error at pi. So I'm just going to punch in e of pi, e of negative pi, and then also e of pi. Those should be equal in this particular case. So notice they're the same. They're the same mainly because your sine function is has some symmetry. It's not always the case that both endpoints are the same. But we can tell 0.524, we'll say, maybe 0.525, just so we round up a little bit. Okay, so this is less than 0.525. Right? So, if we're going to use that fifth degree Taylor polynomial to approximate sine and we're just trying to approximate it in between negative pi and pi, we're never going to be off by more than 0.525. And that 0.525 happening if we happen to use either of the endpoints for our approximation. So let me show you a couple of questions that get pitched at you that make you have to analyze these things graphically. So this one says, determine the range of x values for which the fifth degree Maclaurin polynomial for sine of x approximates sine of x with an error of at most 0.01. Okay, so all we're going to do is we're going to graph our error, which we already have done. Okay, and this is going to go into, like y1 if you're using a graphing calculator. And then we're also going to graph, the horizontal line y equals 0.01. Graph that in like y2. Okay, so I've, again, already done the first part, but let's go do the second part here. Oops, don't want to do that. So I'm going to graph y equals, and it was 0.01. Okay, so now notice, right, this is 0.01 is way down here. So you can just click and find the intersection points. But if we want to look at a little bit of a better picture, I think I'm just going to make my y values not so high. So why don't we make this go to maybe 0.002. And I'll make my y min maybe something a little. This is obviously just optional. I'm just trying to get you to see it a little more clearly. Okay, there we go, a little better. So notice this is like a cutoff, right? So your error, the green, is always less than that black as long as you're in between these two x values, negative 1.761 and 1.761. So that is the range of x values. So I'll just sneak that in here. Okay, so that range of x values is uh, 1.761 and negative 1.761. One little caveat, and it didn't show up on Desmos, but when it comes to this problem, if you're using your calculator and when you find these intersections, the decimals go on, the way to round it is to truncate. Okay, you don't want to round up, because as soon as you round up, you're moving a number like 1.761 a little to the right, and then technically your green would be a little above. So it's the one time where rounding just by cutting, I think what you do in science often, that's what you want to do. So the truncated form of rounding. All right, let me give you a second to try this one if you want on your own, and then so you can pause the video and try it if you'd like, and then I will show you what it looks like. All right, so you hopefully tried it. So again, what we want to do is we're going to graph our error. So our error is going to be e to the x minus we're using our third degree Maclaurin polynomial. And recall that our third degree Maclaurin polynomial is just that. Okay, and so that's going to be in, like y1, for instance, if you're using a graphing calculator, and then you're going to put into another equation y equals 0.02, and then you're going to find the intersections. So let's do that, and I've preemptively done that here. Okay, you might want to play around with the window a little bit. Desmos is more convenient for that. The green is our error, right? I've got my function, my third degree, and I've got my error, and I've got y equals 0.02. So these intersection points are what we want. Any values in between those, the error will be less than 0.02. Otherwise, it'll be more than. Snag that. Okay. So the range of x values are negative 0.867 to 0.867. Let's try one more. And this one I'll try to do maybe a little more organically with you. So same type of problem, just trying to give you a few of the different language subtleties that can show up. So this says, for what values of x can we replace cosine of x by that? That's its second degree Maclaurin polynomial with an error of magnitude no greater than 6 times 10 to the negative 3. Okay, so we're going to graph our error. Okay, our error will just be the absolute value of cosine of x minus, this time I'll just punch it in exactly just to remind you what that is. Okay, that's also known as the second degree. Okay, and that's going to be in y1, or in one equation. And then below that, we're going to graph y equals 6 times 10 to the negative 3. And we find the intersection points. So let's look at that. So I'll just do a new Desmos. Okay, so we've got, we'll call f of x as cosine. And I'm going to call my second degree Taylor polynomial 1 minus x squared divided by 2. And our error is just the absolute value of f of x minus that. Okay, and we don't really need to see the red and the blue. We just wanted them to be stored. So now I graph y equals 6 times 10 to the negative 3. Okay, so we got to adjust our window. Clearly, we can see just our x window really doesn't need to go beyond -2 and 2. So let's do that. -2 and 2. And then for our x values, 6 times 10 to the negative 3 is really small. So we might make our window go from something like, negative 0.001 maybe. And then it can go up to maybe 0.001 here. That's good enough. And here we are. So we're going to click on those points and record them. All right, so what's the question say again? For what values of x can we replace that function with an error no greater than 6 times 10 to the negative 3? Well, for all x in the interval negative 0.618 to 0.618. Okay. If we want to use the if we want to make sure our error is no more than this number, we can use our second degree polynomial, but only in between those x values. After you go beyond that, the errors get greater than what we wanted. So In any case, this should give you an overview of the graphical ways of analyzing the error using a Taylor polynomial. And going forward, we look at the College Board expects a more analytical way of doing it, which we will look at next.